And welcome everyone. In this day 30 learning of graphs, we have already looked at graph representation and basic introduction to graphs. Now we are going to be looking at some common techniques with graph traversal. So there are two common graph traversals techniques that, as you see, I have already written BFS and DFS, which stands for breadth first search and depth first search. B stands for breadth and D stands for depth. So we are firstly going to be looking at uh, DFS, but before that, let's look at the graph that we are going to be working with. So let's consider a graph which has a node 1 and 2. Let me draw it out a little bit more smaller in space. 0, 1 and 2, and 1 connecting to 3 and 4, and 2 connecting to 0 and 5. So 1 connecting to 2, uh, 3 connecting to 1 connecting to 1, 2, 3 and 4, 2 connecting to 0 and 5, and 3 connecting to 1, as that's the only leaf node, 4 connecting to 1 and 5 connecting to 2. Let's consider this as an example. Maybe we can even have this establishment here. So yeah, let's consider this as an example for now. So DFS stands for depth first search. So we pick a node, maybe let's say this as a root node, and we traverse the adjacent node. Let's say we go to 1, and 1 has a neighboring node of 3, and with DFS is usually implemented with stacks. So 1 connected to 3. So 3 is the leaf node. So we come back to 1 and we visit the node 4. 4 has a node of 5. So again 5 has a node of 2. Or we could backtrack all the way from 5 to 4, 4 to 1, 1 to 0, and we could say 1 or 2, 0 has a neighboring node of 2 which is unvisited. So this is the way that DFS works. While on the other hand, BFS has a queue type implementation where we pick a root node and we add it to an unvisited node, that is 0 is unvisited. From this queue we pop the queue and we again add the neighboring nodes which are 1 comma 2, and we pick each element, check if it is unvisited, then we add it to the output of BFS traversal result array, and we pick a specific node, we dequeue it, and then we add in the next set of uh, elements that are connected to it, so which are 3, so 2, 3 comma 4 as part of neighboring nodes or the next level nodes that are part of that are under 1. So next we dequeue 2 and add in 5. So as we do this, we add all of these since all of them are unvisited. So this will be our resulting array in case of BFS. So here is the BFS and here was the DFS idea. So one key thing to note here is BFS uses queue type implementation, DFS uses stack type implementation. Okay, switching here on to the JSPin editor, uh, we have the DFS function, and we have this graph constructed here with this one right here. So, and we are also passing in. So, yeah, so this should be the graph that we are talking about. So, where 0 connects to 1 and 2, and 1 connects to 0, 3, 4, 0, 3, and 4, and 0 is also connected to 2 and 5, 2 and 5, and 3 is connected to 1, 4, 5. These are leaf nodes. So, with this, we are looking for DFS as we just talked about. DFS uses a stack type implementation, which is of first in, last out uh, data structure. So let's go to the two functions that we have for DFS, one with recursive and one with an iterative approach. So let's look at the iterative approach first. We have a stack and a visitor set, which only stores unique set of values. We start off with a start value or a root node, and if the specific node popped out from the stack is unvisited, we visit the neighboring nodes which are unvisited, and we also push them to the stack to explore the path of the neighboring nodes. If none of them uh, add up to unvisited nodes, then we simply pop out of the stack and we continue the exploration path until we visit all of the nodes. So that's the whole idea with DFS. In case of recursive function call, we keep track of a visited set and we continuously make a recursive function call with each unvisited neighboring node. So that's the whole idea again. So if you could see the output here, in case of recursive function, so we start off with a root node which goes to 1, and 1 goes to 3, 3 goes to 1, 1 which goes to 4 again, 4 goes to 1, 1 goes back to pops back to 2, 2 pops back to 5, which is the last node. So that's the way that recursive function call goes. While the iterative approach has a different uh, result. So that's something, the way that it works. But yeah, uh, iterative or recursive functions will give out different set of results. Uh, this traversal technique in either BFS or DFS is intending to go through all the nodes. So that's the whole idea here. Let's go to the BFS breadth first. Search explores all the current node and the child nodes under them. Maybe BFS can also be called as a level order traversal in trees, right? So we have a queue, we dequeue a specific item, and then we add in all the child nodes, and then we unqueue them, and we keep moving level by level until we have all the visited nodes, right? So this is about DFS and BFS. Next, we are going to understand the difference or the uh, scenarios which help or the real places where we can use BFS or DFS. Let's take few examples and let's see where DFS and BFS can be useful. So let's consider a case where we know that BFS is also called as level order traversal. Let's consider we want to traverse from the node 0 to 2, right? So what would be the shortest path, or which algorithm returns the shortest path? So it's BFS because if you see DFS goes through all the nodes and it might take a very long path to reach to 2, right? So while BFS obviously goes through level order and this would directly come here. If DFS, then we need to take all these nodes. Let's say if we are looking for let's say if we are looking for uh, an algorithm which uses minimum space, say, then DFS is better, or having to find end of graph, right? So these are two cases that I can that we can quickly relate to where DFS and BFS can be used. While we are almost done with the applications of BFS and DFS, I even want to have a small touch on the topological sort in which is very similar to DFS. So topological sort is the one other application of DFS. It's similar to DFS. Uh, the whole idea here is, let's consider a practical example where, let's say, in front end, the let's say we want to install a dependency. Let's say we want to install a dependency X. It might also require us to install a dependency Y, and in order for Y to be installed, we also need to have uh, U and V as two other dependencies which has to be installed. Like, in other words, let's say if we want to install the dependency X, all of these three has to be installed. Or if we want to install the dependency Y, then this has to be installed, right? So that's the whole sense of topological sort, right? But it is a very practical example where there might be scenarios like having to learn us in a semester, let's say in a college, a student in first year can either take set of A courses or B courses, right? And these might have uh, which have other set of courses as dependencies, as prerequisites. So this is the whole idea, right? So let's switch to JSPin, but so far we understand topological sort is like a dependency which requires one after another nodes to be traversed, just like a neighboring node which gets traversed with DFS, right? So let's look at some small code snippet and let's quickly wrap this session up, right? So topological sort for a graph, let's say linear ordering of vertex such that every directed edge UV comes with U before V, right? And there is also this word called as directed acyclic graphs. So acyclic means there doesn't occur a cycle, or let me switch back to drawing board maybe for a quick second. So for understanding acyclic graphs, so let's say we have A, B, C, and let's say uh, while D, B, are two different nodes, but if you see here, this gets as a cycle. So this cycling should not be there. Uh, this is cyclic graph. So yeah, that's the whole idea with cyclic graph. So let's switch back to JSPin. So this should be a directed acyclic graph, and let's go with DFS. And if you see here, we have a simple DFS implemented, starting from a stack, which again is a last in first in last out kind of a data structure. We start with reversing a stack, and then we backtrack all the related dependencies that we want to complete to achieve a specific node, right? So we initiate the DFS function here with I, and we keep pushing all the elements to the set, visited set, right? uh, which is required to be completed as part of the specific node, right? So that's about topological sort. We iterate through all the elements, and we check all the specific elements that come before it in an order. Again, topological sort might not be of the same order. The whole idea is to have some sort of a ordering to reach a specific node, or a connected node with all the previous nodes intact, right? Hope you found this video helpful. I've even added few more code snippets which I will attach to the GitHub link with this video description. Please do post any thoughts or confusions or any further explanation needed in any areas. I would be happy to respond in the comment section. Hope you found this video helpful. Until next time, thank you.